Hello all, I welcome you all to the 15th lecture. This course E698M. Last time when we met, we started to talk about thermodynamics and population statistics. I introduced an important concept of partition function, which can also be used for normalizing the probabilities. But what is most important is if there exists several energy configurations, the probability of a particular energy configuration to be occupied is exponentially dependent on the energy value. This is also called the Boltzmann constant, and this comes from the fact that you have so many states which have equal probability of occupation, right? So with that, we derived the Fermi-Dirac distribution using a little bit tricky definitions, but we came to see how this can be derived, and we know that this is used widely in semiconductor device physics. We used or described a few examples of partition function. We took an example of a two-level system, which is most commonly used in many places. If you have time, you should also look at Rabi oscillations and such. If you are interested, just ask me. Maybe I can do a small video on what is Rabi oscillations when you have a two-level system and such. It's much easier in a two-level system. We saw how the population statistics change if I have a quantum harmonic oscillator whose energy levels differ by a constant value, right? We derived the partition function, and then we showed that the effective number of carriers depends on this kind of a distribution, which is typically seen in bosons. It's called as a Bose-Einstein distribution. Apart from that, we saw an interesting aspect of spin, which is an intrinsic property of a particle. In your homework, you will see that there is a lot of similarity between spin and orbital angular momentum. The orbital angular momentum is something which is borrowed from classical physics. That is, if you have a particle which is rotating about a central point r, goes about a momentum p, then the orbital angular momentum is p cross r or r cross p. Both of them are equivalent. And once this is defined, you know how the momentum p has to be defined for a quantum operator. And using that, you can define how L should be in quantum mechanics. And you can see that there can be only integer variations in L because of the fact that the wave function has to be uniquely valued. If I go around this particular, let's say the particle goes around, if it comes back, does a 2 pi rotation, it has to have the same probability here, right? If it comes back by 2 pi, that makes sure that L has some integer values. And if L is an eigenvalue, then there can be several states at which the particle can be, which is given by M, which is taken from 0 plus or minus 1, so on till plus or minus L. So totally you will have 2L plus 1 M states, right? M values for an eigenvalue of the angular momentum. Similarly, between L and S, there is a lot of similarity. S is also an orbital angular momentum, but instead of rotating about a point r, it is just rotating about itself. You have a mass which rotates about itself, right? You cannot take this example too far because this mass rotating about itself already defines that it can be broken down and there is some particular which moves around. You cannot take this much farther, but it can just it can be just assumed as something which is rotating as a top, a top which rotates about itself, right? Something like that. So the S can have eigenvalues half, 1, 2 and so on. If S is half, which is called as fermions, as can be seen, because this M, if S is something like this, M can take values of S separated by an integer. So it can be only minus half and plus half if S is half. If S is 1, it can be minus 1 and 1, right? And so on and so forth. So if M is minus half and half, it's called as a fermion. And we showed that this a particle whose total probability should be 1 now lies on the circumference of the circle. This sphere is called as a block sphere. The eigen functions of the spin state is like this 1 0 and 0 1. And if it is like this, an electron can be written as a superposition of a spin state, and the superposition has two complex values alpha and beta. The summation of these complex values should come to 1, right? And that tells you that any of these superposition states should lie in the circumference, and it is defined by theta, which is separation from the z-axis, and some phi, which is the phase separation, which is a rotation about this, right? Let's say if it is here, you can go around like this, correct? That is this phi. This is called block sphere. It is used when you have two particles which are entangled. If you have a superposition of states, all these things, block sphere is much easier to demonstrate how this works. Now, a particle which spins about itself can be thought about to have a moment b. Mathematically, what is moment? Moment is something which acts about a point, right? So angular moment they call. Why? Because you have a particle which is having a momentum which is rotating about a point. Something multiplied by a distance from a point is called a moment. Moment of inertia, moment of angular momentum, and so on and so forth, right? So an electron which spins about itself has a moment mu, and if there exists a magnetic field, so what happens is it experiences a dipole torque, which is mu cross b. What it means is, if you have a spinner in the block sphere having this direction, the magnetic field will make the spin direction to precess. So this is defined by two values, theta and phi, right, as we saw in the block sphere here. So something like this. If you have a magnetic field, this guy will start precessing with the same theta, but then the phase being different, right, depending upon the magnetic field. And the faster it will spin if you have a larger magnetic field, and so on and so forth. This precession is called as a Larmor precession. The frequency of rotation is called as the Larmor frequency. In addition to that, we introduced what is called as a spin-orbit interaction. This is a behavior in which you have a material which experiences the spin precession even without applying an external magnetic field. How this can happen is when you have a material whose orbital angular momentum is not zero. This is true when you have p orbitals. This is true when you have d orbitals. It is true when you have f orbitals. In all these materials where the valence electrons have a p-type behavior or a L-type behavior, large L value, you have a strong spin orbit interaction. And then we showed that the Hamiltonian can now be described as the Hamiltonian which is periodic plus a small spin orbit component. The spin orbit component is written as gamma L dot S. Gamma L is the actual orbital angular momentum which is acting as if it has a magnetic field. S is the magnetic moment, right? So when you have a spin orbit interaction, the S is called as a spin eigenvalue, is no longer a good quantum number. What do we mean by a good quantum number? Is that it does not have one single value. It is not unique valued. It will keep precision. It will keep preceding, right? Like it keeps moving. In such cases, what is defined is J. J is the total angular momentum, which is summation of the orbital angular momentum plus spin. You can see that it already includes this L dot S component. So if the eigenvalue of S is half and eigenvalue of L is 1, remember L equal to 0 means there is no spin orbit interaction, then you will have just half. If L is 1, you have J, which is half plus 1 by 2 is 3 by 2, correct? So when you have 3 by 2, it's easy to see what are all the values that you can have. M values, right? It can have 3 by 2, 1 by 2, minus 1 by 2 and minus 3 by 2, correct? These are all the values that you can have. So all the valence electrons valence bands which have L not equal to 0 is split like this. So the topmost one here is 3 by 2 plus or minus 3 by 2. This one is 3 by 2. 3 by 2 is the total angular momentum plus or minus 1 by 2. And if it is 1/2, right? So the total, if J is 1/2, then you get the spin orbit split band. This splitting is called as del S naught. The split in the energy is called the spin orbit split band. And this is used in many places, and it's important when we talk about optical properties. We will see later on in this course why this is so important, right? So this spin orbit splitting depends, or it is stronger when you have a larger L component, and that is seen as you go down in the periodic table. Silicon has 0.44, germanium which has a larger P contribution, which has 0.29. Right, as you go down, it has, let's say, indium antimonide has a much higher spin orbit splitting than, let's say, indium arsenide, right? And we saw the band gaps of various structures, and with this we stop our previous discussion, and let's go on to what we were supposed to talk today. So let's start with what we were supposed to discuss today, which is basically band structure modification. So from the last week we spoke about all the things about one single material. Now we will talk about heterojunctions and band structure modifications, because this course is about nanostructures and semiconductor device physics. So we will talk about various nanostructures like quantum wells and tunnel barriers and such, and we will see how we can form them and what happened to these states. So why does band structure typically matter? There are different materials with different band structures. They are used in different properties. When you have a direct band gap semiconductor, it is used in light emission and detection applications, like let's say a solar cell, which is a photo detection, right? It's a photovoltaic, or a light emitting diode, a laser. All of these things are used in light emission applications. Single photon detector, like your cameras, are all in detection applications. When you want to work with high power devices, what is high power? Something which uses large current, something which uses large potential, which should not break down. We use a large band gap semiconductor. What is an example of a large band gap semiconductor? Gallium nitride, aluminum nitride. These are a large band gap, silicon carbide, large band gap semiconductors. An example of direct band gap semiconductor is gallium arsenide, the simplest. A high speed device is something which requires higher effective mass. Why? The mobility mu depends upon the effective mass. Smaller the effective mass, larger is the mobility, right? So materials which have a smaller effective mass, what is smaller effective mass? It is inverse of the gradient, right? So if you have a band structure which has a particular gradient, it is dE by dk. So inverse of the gradient will give you the effective mass. Something which has a smaller effective mass can be worked at much higher frequencies. What's an example of a small effective mass semiconductor? Gallium arsenide is one. Indium arsenide. These are all very good examples of high speed devices. And night vision and IR imaging, it's also a subdivision of this detection, but typically a very small band gap material is used. Indium arsenide is once again an example of a very small band gap material which is used for night vision imaging. And many a times the problem, whatever happens, is that we are not happy with one particular material. We want a combination of properties. For instance, you want a semiconductor which is a good light emitter, and also it should not have large series resistance. It also should have smaller effective mass. It also should have a better mobility. How will you do that? We will show, right? So sometimes when you want to combine 2-3 properties, you need to go to what is called as heterojunctions. When you're going to do heterojunctions, which means that we are going to join 3 materials. So there are different ways to do it. One of the way is called alloying. You alloy two semiconductors. We'll soon see what is alloying. You can grow epitaxially. We saw these things in a few lectures before, how you can grow heterojunctions. Or you can do strained devices. Let's see one by one how we can form each one of them and why each one of them is important. An alloy is formed by mixing two or three semiconducting materials. It can be done in different ways. One is called as a random alloy. This is the most thermodynamic way of mixing two materials. So what it means is, let's say we take an FCC crystal, and if this FCC crystal is silicon, so basically FCC means you have atoms at each of these corners and also in these faces. And an FCC with a motif, most of the semiconductors have atom with a motif, right? So you take an FCC and add another atom to it. If it is gallium arsenide, this guy is gallium and this guy will turn out to be arsenic. When you start to do alloy, what we do is I take indium arsenide and add it with gallium arsenide. Add it with gallium arsenide. What we do is, in a few places, I replace gallium by indium. So let's say this gallium atom is replaced by an indium atom, then I start to have an alloy of indium gallium arsenide. So many a times you will see that I have an indium X, gallium 1 minus X arsenate. This is an alloy of InGas plus gallium arsenide. And this X tells me how many number of gallium atoms I have replaced. Right? So it is 1 minus X is a percentage. If it's a true random alloy, if I take any unit cell at random, the probability to get an indium atom in that point is X%, is X, and the probability to get gallium is 1 minus X, obviously. And we are talking about ideal crystals, so it is only X and 1 minus X. There are no other possibility of finding some other material or a defect or such case. So it can be only indium or gallium. So this is what is called as a perfect random alloy. The another way to mix two materials is when you have a phase separation. What is a phase separation? So basically, I keep adding indium arsenide and gallium arsenide, and the indium goes and replaces gallium in many places. Sometimes it so happens in a material, let's say I have a big 1 centimeter by 1 centimeter long indium arsenide plus gallium arsenide, and I get chunks of indium arsenide and regions of gallium arsenide around it. This is called phase separation. So in these regions, indium did not replace atom by atom, but then formed indium arsenide for a large region. So here the probability to find indium is 1, and here the probability to find gallium is 1 in that same lattice point. This is called a phase separated alloy. The third one is called a super lattice. It is sort of a phase separation, but here the phases separate randomly. In super lattice, you grow in a well-defined fashion. So what I do is I take a material, I grow gas first, grow a thin layer of indium arsenide next, then grow gas, then grow indium arsenide, and then keep growing alternate structures in a well-controlled fashion. It's called as a super lattice. We will soon see how we can use super lattices in our applications. But this is what super lattice is. So whenever we form alloy, the most important thing for a material to be grown in particular fashion is its lattice constant. We saw this previously. The lattice constant determines whether we will be able to grow epitaxially, because there are only a few semiconductors that exist in wafers. For instance, indium phosphide is one, gallium arsenide is one, silicon is one. So there are only a few materials which can be grown on these substrates, and the probability to grow well is given by the lattice constant. Why? Whether if you will be able to grow a single crystal is determined by the strain that the new material will take when it is grown. If the lattice mismatch is large, then the strain will be large and the material will crack. So how do you find the lattice constant of an alloy? It is found by this equation, which is called as a Vega's law. which is given by this. The lattice constant of an alloy is X, that's the concentration that we're talking about, X AM. AM is this lattice constant of the material 1. So indium arsenide has some lattice constant A, gallium arsenide has a lattice constant AM2. So the lattice constant of indium gallium arsenide can be found as X AM1 plus 1 minus X AM2. An example is drawn here. So here I am plotting the lattice constants versus various mole fractions. Let's say this line. This is aluminum indium phosphide. Let's say this line is aluminum indium phosphide. So on the left is basically indium phosphide. On the right, this is aluminum phosphide. And any line, any point in between is some percentage of indium is replaced by aluminum, right? So as the mole fraction increases, X increases, the actual lattice constant goes down almost in a linear fashion. That is explained by this equation, right? So this plot kind of tells you what will be the lattice constant for what mole fraction. This X, which is defined by how many atoms that you have replaced, is called as a mole fraction. This is mostly coming from chemistry. Moles is basically like in a chemical reaction, you have number of moles and such, right? How many react with each other and such. So this is coming from the chemical definition of things. So here there is what is called as a transmission electron microscope image of a well-defined, well-grown random alloy of indium phosphide and indium gallium arsenide. Remember we saw previously the gray scales that you see are uniform across this region, which shows that there is no phase separation. This is a truly random alloy, right? Here you can see this region is truly INGAS. I mean, this paper did not tell us what is the mole fraction X, but you see that you have a very nicely grown alloy. On top of INGAS, you have indium aluminum arsenide antimonide. It's a much more complicated alloy with indium antimonide, indium arsenide with aluminum antimonide. Mixing of indium arsenide with aluminum antimonide. Indium and aluminum share one place, arsenic and antimony share another point in the FCC crystal lattice. The second example of a phase separated growth is this nanowire. Here if you can see, there is a clear separation of phase between this dark contrast which is gold catalyst and this light one which is silicon. So if you see, the silicon gold alloy has clearly phase separated. Gold forms this region separately on top. On the bottom you have this nice wire of silicon. Now that we saw the various physical aspects of alloys, now let's go back and look at what will be its band structure, what will be its band gap, how do we estimate the effective mass and such. Before going there, we have to look at this lattice periodicity of the potential U, right? We discussed this previously. These U's are basically the potential at each lattice point, right? Now we have formed an alloy with A and B. Each one of them will have a different potential. A will have a potential UA, B will have a potential UB, as seen in this figure. You see, A's have a large potential, B have a much smaller potential, right? And if it's a truly random alloy, you cannot tell where A will come and where B will come. And so it is not now true that I have some lattice separation R, U of small r is U of R plus capital R. This is the foundation of the block definition, right? And this will not be true if you have a random alloy, because of the fact that you have these two atoms which are intermixed in a random fashion. So how do we go about this? We electrical engineers and solid state physicists, we like approximations a lot. So what we do is we approximate a new potential such that it is written as XUA plus 1 minus XUB. For many practical applications, it is found that this very simple approximation basically works. It is called as a weighted average, right? So we have a weighted average of these two potentials, and we assume now that we have this unique potential which is constant and periodic throughout space, and once this is defined, we know how to calculate all other things, right? So you have a potential u which is given by this weighted average. If we use this, the band gap can also be obtained by this weighted average xEA plus 1 minus xEB. With these two given, what happens to the effective mass? We define, let's say, the gap or the energy. It is not Eg, sorry, it's not the band gap. Energy of an electron in the conduction band is of course given by this parabolic dispersion. It is h bar square k square by 2m of the alloy. This is the effective mass of the alloy. And as we saw previously, it should again be, let's say, weighted, right? So this equation should also be true. X times h square k square by 2ma. This is the effective mass of an electron in the material A by mb, effective mass of the electron in material B. And this equation should be true. If this is true, we can define the effective mass of the alloy to be given by this particular fashion. So this will be the effective mass of an electron in an alloy. This will be the band gap of an alloy, and this will be the potential in the alloy. Now that we have different alloys and different mole fractions, what happens to the band structure? Will it be a direct band gap or indirect band gap, right? So this is an example of aluminum gallium arsenide. Aluminum gallium arsenide, which is summation of aluminum arsenide plus gallium arsenide, and that is given by this mole fraction. How much? This one, right? X plus 1 minus x. So here I am plotting the conduction band separation at different k space. You remember the high symmetry points that we saw previously? This is gamma, this is L point, and this is the X point. 3 high symmetry points. Please go back and read where are these high symmetry points in the 3-dimensional reciprocal space. You will know where each one of them will come. So as X increases, if you see the gap, the band gap or the conduction band at the gamma point increases, and the conduction band at the X point reduces. So if you cross a particular mole fraction, let's say 0.43 or something here, you see that the band gap changes from a direct band gap to an indirect band gap in aluminum gallium arsenide, because the lowest conduction band point with respect to the valence band shifts from the gamma point to the X point here, right? As long as the band gap or the smallest separation between the conduction and the valence band happens at the gamma point, it remains direct. As soon as it jumps from gamma point to X, then it becomes an indirect band gap semiconductor, right? So the alloying also changes a material from a direct band gap semiconductor to an indirect band gap semiconductor. So while this is true for an alloy, what happens when you have a phase separation, right? Because now you have one material in close contact with another material. You remember we were talking about something, a big sample like this, and a small region which is aluminum arsenide, and region surrounding it which is gallium arsenide. So we have an intimate contact between two materials. When you have something like this, now the band gaps have to arrange among itself. So now the question is, there are different ways it can arrange itself. The first example here is indium gallium arsenide in comparison to the indium phosphate. Indium phosphate is a large band gap semiconductor in comparison to indium gallium arsenide. It can so happen that the conduction and the valence band are much smaller than the gap in the indium phosphide. So when you have something like this, it is called as straddling heterojunction. You see here. So if the band gap in B is encompassed by the band gap in A, you call it a type 1 heterojunction or a straddling gap heterojunction. If the band gap in B and band gap in A has a small overlap, it is called as a staggered gap. if the band gap in B and band gap in A has no overlap. It's called as a broken type. You will see that there can be examples of each one of them here. An interface between indium arsenide and gallium antimonide is basically a broken gap semiconductor. Whereas aluminum antimonide and indium arsenide has this stepped or a staggered gap. And as we saw previously, InGas and indium phosphide has this straddling gap. Right? So basically you can choose the material depending upon the what sort of gap you need. And why do you need this kind of a gap? We will come to that later on. That is the topic of discussion for the next lecture, right? Where we will talk about tunneling barrier, we'll talk about quantum wells, we'll talk about triangular barrier and such. But what determines the way in which these guys sit on top of each other? How do you align these materials? What is one unifying criteria in which you compare two band gaps? What tells that these guys sit like this and not any other way? The rule was given by Anderson. It's called as Anderson's rule. And the Anderson rules it goes like this. When two materials are joined, the vacuum level on either side of the junction should be aligned. This is a very simple statement. This is called as the Anderson's rule, which says that the vacuum level should be constant. And what is a vacuum level? It is the energy of the electron free from all ion core potentials. It is an electron in free space. An electron which is bound has a lower energy than an electron which is in free space. Why? I want you to think about this. Okay, this is something very important. An electron is much better off in an ion core. So whenever you have an attractive potential, total potential is negative in comparison to an electron which is lying in free space. So the vacuum level is among the highest energy of an electron, among the lowest energy when it is in the atom. And electron affinity is the amount of energy released when an electron jumps from vacuum to a material, right? So an electron is now in vacuum and it went to a material. And whenever it goes to a material, most likely it is thought to be in the conduction band, right? Because at 0 Kelvin, all the energy levels till the valence band is completely filled. So you just put an electron in the conduction band. So it is called as the electron affinity. So if you follow this rule of Anderson's, we can clearly see that the semiconductor electron affinity tells you how much the conduction band has to change or should be away from the vacuum level. And now when these two things are set, we can talk about how the bands will meet each other, right? So there are different kind of heterostructures that we spoke about. One is called as a tunnel barrier. One is called as a quantum well. Another one is called as a superlattice and a double barrier. We will talk about this in the next lecture. For now, let's just skip this point. Till now, we have been talking about heterojunctions and talking about electrons in heterojunctions and such. But how do you get electrons in the heterojunction in the first place? You need to dope it. And in a typical bulk semiconductor, we saw about how the bulk semiconductor is doped in EE614. For those of you who have not taken EE614, there are different ways to dope. One is called as alloying. In alloying, you take a semiconductor, you put a metal on top and then you heat it. So what happens? This metal diffuses inside and replaces some of the semiconductor. Let's say this is aluminum and this is silicon. Aluminum will alloy the silicon here and then it will dope it. The same thing you can do with boron as well. You can do with arsenic. You can do with anything. Another one is called as a drive-through metal. So what they do is you take this silicon, heat it. You have a metal disc and then you pass some gas. This gas will take this metal, this dopant into the semiconductor and you get some shape. We saw these things in 614 in much detail. If you are interested, you go and read Semiconductor Device Physics by SMZ. A third way to dope is along the way in which you grow. Let's say you are growing gallium arsenide. You have to give a gallium source which is trimethyl gallium Sometimes they use trimethyl gallium. There are other sources as well. This is the most common source. It's called as a metal organic chemical vapor deposition method. So what they do is they add a dopant gas like silane, silicon tetrachloride, something of that sort, which will replace some of the gallium by silicon by doping it. This is how they do when they are doping. However, the problem with doping is you increase the number of carriers, but you also increase scattering and reduce the mobility due to Coulombic interactions. Hence, the net conductivity, which is proportional to the increase in number of carriers multiplied by the mobility, is lower than what you expect. What we mean is when you dope, you increase the number of carriers n, but because you have added impurities which when they lose they become a charged impurity, scatters the carriers, the mobility will degrade. We will see these things a little bit more detail about carriers and scattering in the next upcoming lectures, but this is a serious problem in many applications. And in heterojunctions, it is possible to have a higher carrier density and not have scattering from dopants which are ionized. This is achieved by what is called as a modulation doping. So, what is modulation doping is something like this. I will go into this drawing the band structure or heterojunction a little bit later, because this is a repetition for people who have already done 614. So I will just do this at the end of this lecture. I will just go to this modulation doping, which is used in a high electron mobility transistor. So here we have heterojunction. We have gallium arsenide and we have aluminum gallium arsenide. And we have a metal. So let's say I'm seeing about this region, right? Don't go there yet. We will come to this gate aspect later on. Here I have a metal. So this is metal. I have gallium arsenide and I have aluminum gallium arsenide and I have gallium arsenide, right? So the band structures are drawn here. I have a metal and n-type, let's say gallium arsenide here. When I have something like this, obviously I will have a Schottky barrier. Why will I have a Schottky barrier here? A semiconductor which is heavily doped, some of the electrons here will jump to the metal whose Fermi level is lower, right? Because here the Fermi level is higher. So when the electrons go here, obviously the conduction band has to bend up because it has lost electrons. So you will have this Schottky barrier and you will have this sort of a triangular potential here. The same thing will happen when you have a all-gas-gas interface. And when you have an all-gas-gas interface, we will see how to draw the interaction between or the band structure between two semiconductors. You will always have a discontinuity in the conduction band as well as the valence band. I strongly recommend you guys to go and look at SMZ and in our previous discussions of heterojunctions. When you have two semiconductors which meet, you will have a discontinuity of the extent of difference in their conduction band energy levels from the vacuum energy level, right? So this discontinuity, if it dips below the Fermi level, you will have a region in which electrons are localized, right? So you will have a conduction band which is lower than the Fermi level. So you will have much higher carrier density here in comparison to any other regions in this material, right? So you have carriers which is localized in this region, but it is not doped. The most doped region here is all-gas, which is not the place carriers reside, right? Because most of the electrons here have now jumped here. Now, because of the fact that the electrons from here have jumped, this band has to bend up. We will see. Probably I should have done drawing the band structure first, but I thought you must have remembered how the band structures bend when two junctions meet. Here gallium arsenide and all-gas meets, and because you have much more electrons here than in the gallium arsenide case, the electrons will jump down. As the electrons go down, the conduction band will bend up. The conduction band bends up to prevent much further electrons to fall down, and you have an electron concentration at the interface between the all gas and gas, right? The same thing will happen here. So here you have all gas and gas, so you will have electrons here at the interface. The most doped region is all gas. You see, the electron concentration is removed from the dopant regions. It is only in these dopant regions that the scattering is larger, right? Because you have ionized dopants here, and the electrons are physically separated from these ionized dopants, and hence you can have a much higher in-plane mobility at these junctions in comparison to the bulk mobility here. And this is how a high electron mobility transistor is typically realized. You have a heterojunction, and the electrons will fall down from a highly doped region to an interface. Now, why do we have a gate here? This gate is used to electrostatically control or electrostatically dispel. Let's say if you want to work with a depletion mode MOSFET, right? If you want to turn this MOSFET off, you use a gate. When you apply, let's say, a positive field here, you accumulate electrons. You apply a negative field here, you will repel the electrons just below the gate. So you will lose any electron carriers that you have at this interface, right? These are different ways in which high electron mobility transistor works, but that is not the purpose of our discussion today. Let me very quickly tell how to draw these band structures, because maybe there might be people who have not taken 614. Let's take the example of gallium arsenide and aluminum gallium arsenide as we saw, right? And the way to draw this is by the Anderson's rule, which says that the vacuum level should remain constant, right? These two. And this is, let's say, chi A, and this is chi B. When you bring them together, you have to ensure, let's say that this the all gas is n-type, as we saw in this example, which is silicon doped. This all gas is a n-type all gas, right? So the conduction band here is, the Fermi level is very close to the conduction band here, and the Fermi level is here for gas, it is undoped, right? Now, when these two come together, if there is no applied potential, the Fermi levels should line up, as we all know. So, the Fermi levels in these two materials will line up. At far enough region, it has to be like this. And remember, this guy is conduction band here, and the valence band is much lower, correct? And because this is n-doped, this has much higher carrier density, all gas has much higher carrier density than gas. At the interface, the band should bend up, right? And here, because at the interface the electrons have jumped from all gas to gas, here the band should bend down. So at the interface you can clearly see there will be a discontinuity. This guy will bend up, this guy will bend down. There may or may not be a discontinuity in the valence band. Most likely there will be a small discontinuity in the valence band as well, but in the conduction band there will be a discontinuity. And if it extends to be something like this, you get let's say a 2-deg here. This is called as a 2-dimensional electron gas, right? So this is in short a summary about how do you draw the band structures. You start with the assumption of Anderson's law. However, the Anderson's law is something which is not known to be true in many cases. This happens because an electron at the surface, when you join, do not see a vacuum at all, right? Because it sees another material, and when there is another material, there are charges, it has a different dielectric constant, it is a very different electric atmosphere, and hence the thought of vacuum level very close to the interface does not make any sense. It has a very different work function, it has surface potentials, it has charged surface, and so many factors. So the Anderson's law, or the way in which this is typically done, though it works in many cases, particularly for semiconductors, this does not work very well. There is another law which is called as a Schottky-Mott law, but we will not go into those details right now. Okay. So now that we saw heterojunctions, we saw how heterojunctions are formed. Now we will look at another heterojunction. So basically we saw a random heterojunction where you have different band gaps depending upon the mole fraction. We saw the situation where we have phase separation. We have two materials in close contact, and now we will see strained heterojunctions. The most commonly used strained heterojunction is silicon germanium. We have seen people use silicon germanium in high-speed transport devices because they have found that if you have tensile strain, you will have better mobility. So people tend to work with different materials to work, with different alloy concentrations of silicon and germanium. At room temperature, silicon lattice constant is 0.543 and germanium lattice constant is 0.564, right? And the band gap of silicon is 1.12 and band gap of germanium is 0.66. Let us say that you have a substrate which is something like this, and you grow on this substrate whose lattice constant is smaller than the substrate. You get what is called as a tensile strained film, one on top of the other, right? And the band structure of this particular film looks like this. The conduction band is something like this, and the valence band, which is in an unstrained situation, so here it is unstrained situation, it's called homoepitaxy, the same lattice separation on the film as well as on the substrate. Let's say the band structure looks something like this. You have a heavy hole, you have a light hole, you have a spin orbit split hole. If the film has a smaller lattice constant than the relaxed structure, you have a valence band configuration something like this. When your film has a larger lattice constant than the substrate, you will have a very different valence band configuration which looks something like this, right? So your heavy hole and light holes are now largely mismatched, and you can see that you have very different hole mobilities, right? So your hole mobility is something like this, your hole mobility here is very different. Once again, when you have this silicon germanium heterojunctions, you have different sort of heterojunctions when you have phase separation. So here you have silicon and silicon germanium in a strained layer. The band structures are slightly different, and you can see how the junctions form. Most of the cases you have a stepped junction in a silicon germanium heterojunction. One can also form one-dimensional and zero-dimensional structures when we form these heterojunctions. Here are the examples of forming a wire and a dot. I am going to give this as a part of your homework. So it is not a big difficulty. What people typically do is you take this kind of a material, and as we saw previously, if I have an all-gas layer on top of a gas layer, you will get a two-dimensional electron gas at the interface. One can remove the all-gas layer selectively, and what happens is that the two-dimensional electron gas, which should be a plane in 3 dimension, can now be reduced in the second dimension as well to give you a wire. Instead of a 2D plane, you can remove that region and then form. You can localize the second. Okay, let me draw this. So let's say this is your 2D electron gas, right? So basically this is infinite in 2-dimensional space. If you can actually localize this region, form a rib like this, you will get a wire. How you can do this? What you typically do is you remove the all-gas layer from the top in certain regions, making the all-gas layer exist only for some region. The all-gas region is the actual n-doped region which gives you the electron to form the 2-di in the first place, right? So you remove the material, you will get a wire. To get a dot, you remove this as well, finally having only this region in the center. you get what is called as a quantum dot. So based by using nanofabrication methods, one can form a quantum wire or a 1D structure or a 0D structure, which is called as a quantum dot. So with this we will stop today, or at least this part of the lecture. The next time we meet, let's talk about actual some, let's say, band structure or wave function calculations for certain potentials. The first few lectures we saw about artificial infinitely deep potential wells, but when we make these heterojunctions, you can clearly see that the potential wells or the band structures do not have infinite potential differences. We'll have a finite potential wells. We will see a solution for a finite potential well, and we will also see a solution for, let's say, a triangular potential well. So we'll stop here. Thank you.